So this chapter is also rather short, but wants to look more specifically at climate change and the carbon dioxide increases which are causing most of the climate change, and public health. It's a plant biology perspective coming from Louis Ziska and Christy Eby, who have done a lot of work in this direction. So they look at the direct impacts and the indirect impacts. So direct impacts include things like the carbon fertilization of the plants, changes in plant production of pollen and spores that live on them, contact dermatitis and other things that may change because of CO2 increase and plants' response to the CO2 increase, and indirect effects on things like food security, nutrition, toxicology, pharmacology. Pharmacology is the drugs and the interactions with humans. Toxicology is, of course, the production of toxins and how toxic they are to humans, and so on and so forth. So we'll just look at some examples. A lot of this is kind of potential pathways through which climate change and CO2 can affect plant phenology, life cycles, pharmacology, toxicology, and their impact on health outcomes like contact dermatitis and so on. And then we will see whether that can convert into part of this One Health perspective on climate impacts and planetary changes on human health. A good example to start with is, of course, ragweed pollen season, which is very nasty and very common in mid-latitudes. So this is data from 1995 to 2011 as a function of differential surface warming with latitude, showing the US. So it's showing the change in length of the pollen season. Way south here, there's been a 1-day decrease in the pollen season, but in general, as you go north, there has been increase by various days up to 27 days up here in Canada. Okay, so this is not fun, right? If you are somebody who suffers from allergies like ragweed pollen, and you are going to have 27 more days of pollen season in a year, that's going to be quite a torture for you to be outside, to be functional, to be surviving the itchy rhinitis, eyes, and breathing troubles, lack of outdoor activities, and so on and so forth. Allergies do cost a lot of money. It's tens of billions of dollars every year for the US healthcare system, so it's not a joke, especially when these can get exacerbated by enhanced ozone, low-level ozone, and heat waves, and so on and so forth. Okay, the other direct trends also include the global megatrends in biodiversity and public health. So we are looking here at 1970 to 2010 or so, and 1960 to 2005 or so. In A, we are looking at declining biodiversity as percentage change since 1970, as measured by two indices. WPSI is the Waterbird Population Status Index, so that's a biodiversity index there. LPI is the Living Planet Index. I won't go into the details, but you can look up this reference, and you can see that there is a significant drop in biodiversity as measured by these two metrics, and correspondingly, there has been an increase in asthma and allergic rhinitis, which is pollen and mold and fungus-related responses in the respiratory system. So increasing trends in prevalence of inflammatory civilization diseases, asthma and allergic rhinitis among military conscripts between 1966 and 2003. So obviously trends always correlate, but this is the point of looking at the impact of CO2 on plants and human health. Okay, so obviously there is a broad change in temperature, precipitation, growing length of the growing season, extreme events, and so on. But here there is an attempt to make more connections. There have been experiments done growing various plants in chambers with increased concentrations of CO2. So a lot of this data is specific to CO2 impacts themselves. Looking at more of this, various countries here, Belgium, Canada, Finland, France, Greece, Korea, Poland, US, Russia, and so on. And looking at change in pollen load per year in percentage and slope of cumulative temperature increase. So there is significant correlations between increasing temperature and pollen load per year, change in pollen load per year, and slope of cumulative temperature increase again here. So you can look at these various countries that are listed here. This is corresponding to T max cumulative temperature increase. This is corresponding to T min cumulative temperature increase. Obviously we talked about how T min is increasing faster than T max and the daily temperature range is decreasing. Health outcomes often actually depend on temperature, diurnal cycle of temperature, including vector-borne diseases like mosquito cycles, which are dependent on diurnal cycle. Okay, so this is frost-free days, an increase in pollen load per year. Frost obviously acts as a control on plant processes and phenology and pore production and so on. So there is a significant correlation there. This is again increase in pollen season duration in days per year. This is increase in pollen load per year with respect to frost-free days. This is change in pollen season duration versus slope of cumulative change in temperature above freezing, and slope of cumulative change in temperatures above freezing versus change in pollen season duration. So you can see that the manifestations of CO2 are going to be either direct onto the plants. I think you know what CO2 fertilization is. Basically, the stomata have to open to capture CO2 to produce carbohydrate during photosynthesis by taking sunlight through the chloroplasts, and they have to bring up nutrients and water from the roots. And they want to open the stomata just long enough to capture enough CO2 without losing too much water, because water is a precious commodity for photosynthesis as well. So as CO2 increases, the data shows that stomata don't have to remain open for so long because there is high CO2, and that leads into lots of changes, including water not being used and being released back through the roots and affecting soil moisture, soil hydrology, and so on and so forth. And of course all the other metabolic processes and reproduction, flowering seasons, pollen loading, etc. Everything changes with CO2 increase indirectly as well. The other nasty thing that happens with CO2 increase and warming is the production of mold and fungi, and this is Alternaria alternata, the lesions. It's a spore producing blight. This is affects leaves, and then it lives on more than 150 species. So the number of spores being produced and released into the air is increasing with temperature and CO2, and this is obviously a serious health concern for many people. So that's something that's directly affecting plants and health, but indirectly from CO2 to other environmental parameters and so on. Okay, so this is similar to what we looked at in terms of harmful algal blooms. There are various manifestations of environmental change which affect harmful algal blooms, and there are various manifestations, direct and indirect, of CO2 impact on plants and health outcomes or processes that affect health, like pollen loading and pollen season, growing season, mold, spores, fungi, and so on.